energy. Using laser scanning technology, the team assessed the damage underwater. The subsequent recovery mission was textbook.
A marvel of engineering, ready for deployment.
Lower the array to 50 meters. Maintain tension on the line.
Control, this is Pelican 1. We are beginning our descent to the target depth. All systems green.
Lower the ROV slowly. Watch the waves.
Ropes clear on the starboard side.
Smeller a ton. As the ROV descends further, its powerful beams illuminate the tail section and wings of the modern fighter jet.
We see the robotic arm approaching the main fuselage of the sunken fighter. The goal is to secure this piece of debris for transport back to the surface.
The ROV successfully retrieves the metal fragment, carefully placing it in the bin. Next, the suction tube activates.
The deep-sea vacuum disturbs the silt, sending the crabs scattering as we approach the dark, ribbed interior of the sunken aircraft.
As we move further into the main fuselage, the spotlight highlights the intricate structural frames, encrusted with years of silt and rust.
As the debris is cleared, the intricate design of the turbine blades within the engine intake becomes visible for the first time.
The specialized probe makes contact with the sunken C-130.
The robotic arm, designated CHAR-3, is now deploying the rhodamine die near the tail section, or beam.
The CAR-3 system uses a sophisticated suction mechanism to secure itself to the encrusted fuselage, allowing
The massive C-130 Hercules now rests tilted on the abyssal plain. The ROV's, designated Chahar-1, the manipulator's brush attachment spins rapidly, kicking up a significant plume of sediment as it reveals the aircraft's surface for the first time in decades. The specialized shears of the ROV apply immense pressure, finally severing the encrusted netting and freeing the landing gear.
Here we see the ROV scanning the pilot station. The laser provides a highly accurate three-dimensional model of the debris field.
The structural integrity seems compromised around the main fuselage. Adjusting the scan angle now.
We are getting a close-up view of the mechanical components. The level of rust and marine growth here is extensive, nearly obscuring the gears entirely.
The ROV's manipulator arm engages the specialized drill, slowly working to remove the corroded panel and access the aircraft's crucial systems.
To ensure they can return to the site, the team uses the ROV to release a pressurized yellow marker buoy attached to a thin cable.
Lowered by heavy cables, the specialized recovery frame approaches the BG-1 aircraft, which has rested on the seabed for decades. The massive yellow structure begins its descent, carefully maneuvering towards the delicate, silt-covered fuselage of the aircraft below.
The manipulator arm successfully latches the heavy hook onto the fuselage. The cable strains under the tension, confirming the connection is secure.
With millimeter precision, the robotic arm secured the primary lifting hook to the aircraft's nose section. The salvage operation could now begin. With precision control, the team maneuvers the grapple into the forward intake. The sudden release of air confirms a successful connection.
The ROV's hydraulic cutter engages the rusted cable. As the pressure builds, the metal strains, culminating in a burst.
As the pressurized air fills the massive lift bags, a powerful torrent of bubbles erupts from the valves, marking the start of the salvage operation.
The structural integrity model confirms our findings. We have major corrosion on the starboard wing, section Charlie.
Kicking up a massive plume of sediment, the aircraft slowly begins its ascent from the dark seabed.
The massive jet remains suspended above the seabed while the ROVs inspect the lifting cables.
The salvage operation relies entirely on this connection. The white braided rope is vibrating intensely.
After weeks of preparation, the delicate process of lifting the sunken Harrier begins, utilizing these two massive buoyancy aids.
Roger that, steadying the approach.
With the orange lift bag fully inflated, the ROV performs a final inspection of the straps before the ascent begins.
The forward strap looks secure, but check the tension on the rear one.
Roger that. Canopy looks intact from here. Keep the tension on that side. I'm almost there.
Okay, it's holding firm. How many more clicks?
Just one more to lock it down.
All right, keep the pressure steady. We are almost through the main spar.
We have visual confirmation. The fuselage is clear. Continue the hoist. Advise the bridge we are secure.
This specialized transport vessel, designated BG-2, carries the Harrier.
Easy now, bring her down slow.
Clear on the starboard side.
2 meters to touchdown. Surface, the shackle is set. I'm testing the connection now. Stand by for tension.
This massive naval salvage ship, the BG-3, is equipped with a Harrier jet and high-volume pumps capable of moving tons of water.
This thick chemical agent reacts directly with the corrosion, a vital step in maintaining the structural integrity of the aircraft in harsh marine environments.
Watch your step. Secure that connection point now.
It's fastened. Bring the next pole over. Come on, break free. Oh no, look out!
Pull it tighter. We need another bungee over here.
I've got this side hooked. Watch the edge.
Watch the wind. Pull it down towards the frame.
Okay, I've got the first cord hooked.
Good, let's get the other side done quickly.
And that is locked in. We can't afford any movement out here.
Keep her steady, Captain. The tarp on the starboard side is coming loose near the tail.
Bridge to barge 2, maintain current speed. We have a clear signal on the telemetry data now.
Heave on that line. Got the loop over the bollard. All right, pull it tight. She's almost alongside.
We're clear on the tail fin, but watch the intake.
I see that. The telemetry shows we have 3 inches of clearance.
All right, let's proceed slowly.
The bore scope allows us to examine the turbine blades for microfractures without disassembling the entire unit.
Descent looks stable. Engaging final sequence now.
Copy that. Moving to secure the starboard side. Descent speed steady. You have 3 feet remaining.
Confirmed. Coming down slow. We are seated.
Did you get the inboard flap section yet?
Almost. Moving to it now. This coating is tough.
The high-pressure steam nozzle effectively removes even the most stubborn, barnacle-like deposits without damaging the fuselage.
You have to be real careful with the composite. Use the plastic scraper, nice and slow, otherwise you risk damaging the surface.
Pressure's holding steady at 50 psi. Roger that. No leaks on this end.
Almost there. Set the brake. Brake set. Hand me the coupling. Watch the seal. Okay, tight.
This is the B2 ram sample we recovered from Hangar 4. Notice the textured surface of the material itself.
As you can see, the mud is extremely thick here. We use the high-pressure vacuum to break it down without damaging the insulation.
Here we are applying the corrosion inhibitor to the BG-3 fuselage. This protective layer is essential for preventing rust and extending the life of the aircraft.
The actuator looks good. Torque set on bolt 4. Copy that. Logging the procedure now.
Initiating flush sequence. Note the initial dark coloration and high pressure spike. Fluid is beginning to clear now. System stabilization confirmed.
You can see the fluid moving rapidly there. We have to ensure this coupling is torqued precisely to avoid any pressure loss. Make sure you get deep into those grooves. The grease really builds up there. See how clean that is now?
The laser scan is complete. We now have a full 3D model. And as the monitor confirms, the status is cataloged.
As the probe passes over the rivets, the waveform indicates the structural integrity of the metal. The technician uses the NDT probe to scan for microfractures near the rivets, a critical step for maintaining structural integrity.
Look at the detail on this fracture near the bolt.
Right. It's significant. We'll have to rerun the analysis on the mobile unit.
As we adjust the focus, we can clearly see the crystalline structures within the sample.
Scan complete on section 7, all readings stable.
Confirmed. You are clear to proceed.
Okay, lower impact by 2 degrees.
2 degrees confirmed.
Watch the clearance on the port side, almost there.
Okay, that did it. Let's lift from this side. Right, easy now. Watch your fingers.
The AN /H says AVG 8 exposed. I dropped the wrench. I think it went all the way down.
Again.
All right, let's see if we can spot it from here.
Keep it steady right there. Confirmed. We are fully down and locked.
Excellent. Another perfect extraction.
Okay, bringing it up slowly. Watch the clearance on the right side.
We're pulling the main harness now. It's critical to ensure no strain is put on the connectors during removal.
Beginning the separation sequence now. Power stable.
All sensors are within tolerance. Proceed with caution.
Clear path overhead.
A little lower on your side, Mark.
Copy that. Easing down now.
Looks good from here.
The specialized team meticulously removes the damaged composite, a critical step before the structural integrity can be fully assessed.
The ultrasound probe sends high-frequency sound waves through the composite, allowing us to visualize internal defects on the thermal map.
The handheld scanner allows us to perform rapid, non-destructive testing on the composite materials. As you can see,
We use the digital calipers to ensure precise placement within the millimeter.
To analyze the structural integrity, we use this specialized bit to take a core sample, minimizing debris with the attached vacuum system. This one is seized pretty tight. We apply torque until the corrosion breaks free, then carefully wiggle it out for inspection.
Here on the borescope, you can see the extent of the damage. This debris is causing a blockage. We'll use the retrieval tool now to carefully extract this honeycomb seal.
We're checking for continuity. The OL reading means we have an open circuit on this pin. We'll move to the next one.
This close-up reveals the extent of the damage. The laser scanning confirms the complete failure of this trace due to severe oxidation and corrosion.
Structural weakness detected. Replacement required.
This is critical. I am seeing a major structural weakness on the main turbine shaft.
Watch the clearance on your side. Clear. Clear. Bring it down slow.
We use the probe to check for microfractures along the seam. The light highlights any imperfections on the polished surface.
We'll use the power drill to loosen these housing bolts. Now carefully lift the casing, and as you can see, the planetary gear system is fully exposed.
The key to a successful rebuild is organization. We inspect each gear and shaft right here before it goes back into the assembly.
And with that tap, the restoration plan is officially approved. We can now move forward.
The key is maintaining a steady hand while the vacuum system ensures no harmful dust escapes the immediate area.
Here in the finishing area, precision is everything. This orbital sander ensures the aircraft part meets the exact specifications required for flight.
Keep pushing. It's clearing the threshold now. Almost closed.
The components undergo extensive immersion testing, but it's in the NDT lab using ultraviolet light.
As you can see, the fluorescent penetrant reveals a critical flaw right here.
Our robotic cells manage the initial high-intensity welds before moving to the skilled hands of our technicians for final assembly.
Precision is paramount when seating the bearing. As you can see, the vibration analysis is well within tolerance at this RPM.
From the high-velocity spin of the turbine to the precise work of the assembly team, every stage is critical for performance. From the precise manual assembly of the wire harness to the automated testing of the populated circuit boards, quality control is paramount. Precision is paramount. Whether testing sensitive electronics or assembling complex engines, automation drives efficiency across the manufacturing floor.
Precision is paramount at the assembly station. Once secured, the components move to the foundry, where the superheated metal is tempered in the quench tank.
Once quenched, the frame is ready for assembly. where our technicians ensure millimeter-perfect accuracy.
In the electronics lab, the new avionics suite undergoes rigorous testing before integration onto the fuselage in the main hangar.
This massive composite fuselage represents the future of aviation. But even with advanced technology, from survival gear packing to the precise application of advanced composites, every step here is critical for mission success.
Keep the temperature steady on that edge. Applying pressure now to smooth the surface.
After the compounds are thoroughly mixed by the automated system, the specialized primer is applied to the fuselage in the main hangar. Airframe. Applied in thin, even coats, the primer ensures long-lasting durability. Then
there.
Clear on this side, boss.
Steady, steady. Lower it 5 more feet. Okay, team, bring the starboard side down slowly. Keep that laser aligned on the mark. We are within 2 millimeters.
We compare the scan data against the CAD model. Looks like the adjustments were successful. All parameters are within tolerance now.
The final impact secures the main strut, ensuring the assembly is locked in place.
Slowly maintain alignment.
Hold it there, bring it slightly to the left.
Confirmed, easy down.
The BG-45 inspection area requires absolute sterility. High-resolution scans ensure every surface meets.
We slide the unit in, making sure the harnesses are clear, and then torque the fastener until it clicks, verifying the connection.
Pre-flight checks initiated. Auxiliary power engaged. Systems coming online.
Ground crew safety is paramount during taxi operations on the flight line.
Every inch of the aircraft must be checked. Using specialized equipment, the team ensures that the internal components are functioning.
The avionics software undergoes rigorous coding before being loaded directly onto the aircraft's flight systems via the maintenance port.
By the authority vested in me, I hereby affix this seal and confirm the validity of this document.
The folding wing mechanism is essential for carrier operations. As you can see, the hydraulics engage smoothly, even with the afterburners active.
the ground power unit is essential for the pre-flight checks, ensuring the avionics are fully operational before engines start.
Power levels are nominal. Initiating the fold sequence now.
System check initiated. All parameters are currently reading nominal.
INS calibration complete. All systems green.
I'm almost done with this section.
Copy, the upper fuselage is clear.
As the landing gear locks into place, the Raptor achieves its optimal aerodynamic profile for supersonic flight.
There they are, 3 Bandits, 25 miles, heading 090.
The curing process uses infrared heat lamps to strengthen the composite materials of the wing structure.
And that should hold firm for the next service interval. The key is ensuring a smooth application without any air pockets.
Look at the fluctuation here at Mach 0.8. It correlates directly with the intake temperature.
Yes, but the latest software update should stabilize that during the next flight envelope expansion. Fuel gauge reads 100%.
Roger that. Fueling complete.
We have to check every panel, every rivet. This flashlight helps us spot the hairline cracks you'd otherwise miss in the shadow of the wing.
The sensor output on the auxiliary control unit is fluctuating.
It's correcting now.
Initiating the final systems check.
Switching to internal power. Avionics initializing. All systems green.
We have ignition. Thrust levels spiking at T4.
Confirming readings. Maintaining sequence. Go for afterburner test.
Okay, cycling complete on the starboard side. Deflection angles are nominal across the envelope. We are green for taxi tests.
Keep her coming straight. A little slower now. Hold. Stop.
This iteration shows a 40% increase in fuel efficiency due to the redesigned fuselage structure.
And the thermal signature is significantly lower than projected.
Wait, that variable is undefined. Let's trace the input stream again.
Ground test passed. All systems GO. Software update successful. All systems nominal.
Okay, the transfer is complete. Cable pulled.
Checklist complete. Systems nominal. Requesting clearance for immediate takeoff. Radio check. Loud and clear, cleared for taxi.